So I'm going to talk about unobtrusive measurement. Let's see, the first disclaimer of several, I think, during this talk. Much of what I'm going to discuss is very Linux specific, often x86-64 specific. It's not to say that these ideas aren't possible to port to other systems, but I'm going to address Linux specific interfaces for the most part. Let's see. So first of all, let's just talk about tools that we typically use inside the VM for getting some ideas about the performance of our systems. So you're probably familiar with fprof, eflame, and other things like this. The thing about these, they're all built on the tracing facilities in Erlang, and of course, as kind of we've heard throughout the weekend, the tracing facilities in the Erlang VM are great. They're extremely flexible. The problem is that beyond a certain point, they aren't all that safe. They are somewhat obtrusive. I guess I'll show. Basically, for us, profiling in production is hard. You can see this is sort of like a typical machine in its idle state, right? It's like a load average of 50 and so on. And basically, in a lot of ways, it's really there isn't a lot of headroom. And it turns out, especially, so the systems that I work on are dealing with tens of thousands of requests per second, and they're in this kind of dynamic relationship with other systems, so that if you slow down one node too much, queues build up, and basically things go haywire, and everything has a very, very small latency window. So, and it turns out that for the most part, it's very easy to blow one of these systems away by turning on tracing, let alone some of the other mechanisms that are available. And I should say the disclaimer, of course, with OTP 19, which I have not tested yet, there are more facilities for doing tracing safely, like as Lucas Larson talked about, and I'm really eager to explore some of those things, because the more that we can make in-VM tracing safe, I think the better it's going to be. Although I will say that, well, let's talk first about basically the idea that, so if we're not going to trace in the VM, sort of how far outside could we go? And I wanted to mention this great paper, Zero Overhead Profiling via EM Emanations, which is pretty far out there, but is the idea that you can actually profile a system just by measuring the electromagnetic emanations of your hardware. Of course, our machines are in data centers, so that's not really an option. In the embedded world, of course, there's various hardware-assisted profiling approaches. I mean, the closest we have, Intel server processors have a lot of really handy performance counters and things like processor trace, last branch record, things like this, which are useful, but still not exactly what we're looking for. So we know that we're going to have to cooperate with the operating system. But it turns out that this is actually quite useful. So under Linux, we have we have many different interfaces. This is actually only scratching the surface, but there are many different operating system provided facilities for doing various kinds of inspection of processes and things like that. So there's ptrace, ftrace, system tap, and perf events are four that I'm going to talk about briefly. So ptrace, I think, is really the traditional approach, and part of that is because it's portable. Pretty much every Unix has some variation on this API. It's used by GDB, strace, pstack, many tools like this. Now, the problem with ptrace is that it actually stops processes when, in order to do anything, basically, ptrace has to attach to that process, which means stopping it, which typically for us it just takes down a node in a matter of a few seconds, because it just introduces way too many interruptions. Especially, it's really disastrous just trying to strace a system call. If you're trying to strace a system call, what basically happens is for every system call, your process stops. The strace process gets woken up. Strace does some work, then it wakes your process up again, and this is really not fast. Even if you're only filtering to a few system calls. So ptrace is pretty much unacceptable for us. And actually, this is it's interesting. Anyone who saw Eric Stenman's talk yesterday, he gave a nice little GDB invocation to show the backtraces. And of course, this is really nice, but I can't do that on these systems because GDB will stop that process just for long enough to do the backtraces. But it turns out that actually is enough to set things a kilter. So ptrace is out, and just a note about procpid mem. So procpid mem is a special file for each process, which is actually the memory, a file that represents the memory of that process, the address space of that process. But you can't read from it without stopping the process. So it's basically the same as the ptrace situation. Linux did add ptrace Cs recently, but it still doesn't alleviate this problem. It allows you to do some ptrace operations, but not actually the things that you're interested in, like especially getting the registers, getting the stack, things like that. So slightly less obtrusive. You have ftrace, which is a really nice facility for system call tracing. And basically, sort of loosely, it operates by sort of every I guess every kernel call has like an insertion point, which I guess is probably a NOP sled that you can specify sort of what calls you're interested in, and then it overwrites the NOP sled just for those calls and collects some data. And this is certainly a lot safer than strace. And one thing which I'll also talk about sort of near the end, some possibilities for this, but it's very useful for tracing mmap calls, which if you're trying to track down memory fragmentation issues, the allocator stats from the VM itself are not the whole story. So that's really interesting. But we're interested in more user space stuff. So the next thing, and kind of the obvious thing, and the thing that I tried to work with here was system tap. And this, I think, maybe is the second or third disclaimer, which is, of course, probably some of you out there work with dtrace on other operating systems. There's a continuous competition between these things, but it seems evident that especially dtrace has this whole system of ustack helpers and things like this, which don't seem to really exist in system tap. It's definitely not as safe as dtrace, or at least it has been for me. So the way system tap works, you write in this little scripting language. It translates that into C that gets compiled into a kernel module, which gets inserted into the running system, which obviously already is a bit sketchy for your production systems. But then also, so it has throttling. It has some concepts of throttling, but for me, it didn't work so well, and certainly wasn't confidence-inspiring, the ease with which one can take down a system with it. I understand dtrace is safer and can do all the same things, so that's a possibility on other operating systems. And yeah, and you build a VM with -- with dynamic trace and either dtrace or system tap. The nice thing about this is it inserts a bunch of probes. The couple of useful probes, like there's these GC probes, which I think are probably the most useful of the probes that are provided. You get some information about where GCs are starting and ending, how much was reclaimed, things like that. And that's actually, it's not too bad probing that stuff in terms of its overhead. Another one is useful one in lib runtime tools examples. They have this memory one, which like for process heap, grow, and shrink. This is like slightly more expensive, but just gives you an idea of this is what like a system tap script looks like. And sort of some of the tools that I'm going to talk about later, I probably could have implemented as system tap tools. I just didn't have the confidence in it as a safe thing to use in production, and also it is kind of complicated. Hopefully that's a situation that's going to improve over time. And so finally, the least obtrusive sort of facility that we have access to is the perf events facility in the Linux kernel. So yeah, so originally, and this is why you have similar facilities in, for example, in the BSDs for reading the hardware performance counters in various processors. I'm specifically thinking about the Intel family of modern server processors, where they keep adding more and more interesting performance counter facilities. But so the original goal of perf events was just to give user space access to these facilities, but it grew the ability to sample registers and stack, which turns out to be incredibly handy because also it's designed to be really safe. So there are all sorts of sort of self-checks and balances in that code, especially the code where it's doing sampling, and it will throttle itself. And there's a nice little sort of system by which your user space program gets to know that you lost events because it was throttled and you're sampling too fast for the system and so on. And I've even I've felt safe enough that I've really cranked up the frequency on sampling and still not taken down a system yet. So and had perf events save me from myself. So this is already a really nice aspect of this, and it can sample quite a lot of things. Although what we'll notice is the facilities are basically designed around the perf tool, which is probably what you're more familiar with, the user space tool that comes with the kernel that is the primary interface for this. So a lot of the facilities, for example, it would be really nice. Perf has the ability to sample mmap events, so it would be really nice if we could actually, use this instead of ftrace for sampling mmap calls specifically. But it turns out that entire facility only gives us mmap syscalls for executable pages because it's only designed to allow the user space tool to look at new binaries as they get paged in. And so there's a lot of things like that, facilities that are almost really good for our general purpose, and we'll see how we can bend some of them for our more dynamic language, but it's mostly really designed around that. And even though it is fairly unobtrusive and scales back, I should mention that it does also have overhead. Vince Weaver did this great write-up of, and this is kind of inherent in anything that we're going to have that is running at the operating system level. Basically, because perf changes the cache behavior of your application, because it touches memory in certain ways, you just are never going to have exactly the same performance and cache behavior as you would have ordinarily. So obviously, for really, really performance-sensitive applications, this is not adequate. But for most things, I mean, if you're already, unless you're running a tickless kernel and your processes are running uninterrupted, you probably already have the kernel scheduler butting in periodically and a lot of these effects anyway. So compared to any of the other facilities I mentioned, the overhead is much lower. So before talking about some Erlang specific things, I just wanted to say, like, even for Erlang, the native tools that are just designed for really oriented towards profiling C code are really handy for Erlang code too. They still tell us a lot about what the VM is doing, what your code is doing. Perf itself just has so many features, and also like there are various offshoots of this. Brennan Gregg has written lots of tools, the perf tools and other things that use ftrace and perf and system tap, and these are really useful for kind of spying on your system and getting an idea of what's actually happening. Yeah, something I should have mentioned is, like, this is the other reason to, I think a core reason aside from unobtrusiveness to occasionally think outside the VM and not just do measurements from inside the VM is that when you actually see the native workload, you often get a better picture. In-VM tools can often hide the true nature of what's happening on the system, and it's only once you actually see, so for example, we'll actually look at, so perf top is just a really convenient interface to perf that is like top, but it's actually showing us sort of where basically every time it's sampled, what process was running, what the program counter was, with a symbol ideally if we have it, and So like in this case, we're looking at the Erlang VM. We can see we've got a bunch of NIFs that are taking a fair bit of time. So obviously, and this is a common pattern you'll usually see, if you're actually bound by bytecode evaluation, then process main is going to be at the top always. That's the core sort of beam evaluation loop. And so that's also what we're really interested in if we want to characterize the Erlang workload. But even that said, there's still really interesting things here. We can see like copy struct, copy shallow, Ertz garbage collect. There's often like EQ and CMP are usually in here too. These are often really interesting because they often tell us, for example, well, we probably have too many records that we're modifying instead of, and creating a lot of garbage. Especially, we're probably garbage collecting too much if Ertz garbage collect is that high. What else? You often see the memory allocator functions, like especially finding best fit functions and things like that in this. That can often give you an idea of, do you actually need to, for example, resize the process heap when you're creating certain processes, or so there's a lot of useful ideas that can come up from looking at that. Another great visualization, sorry, this cut off a little, that sort of comes out of, I guess it may have been invented by Brendan Gregg, but he certainly has been a great popularizer of it, is this concept of flame graphs. I think I have an interactive one here. Let's see if we can see anything. Sorry, it's cut off at the bottom. But it's this visualization of call stack, sometimes unfortunately missing a lot of symbols. But basically, which is this visualization of how different functions within the over this period of time have spent time. And what's really nice is there's this great SVG visualization that is interactive, where you can sort of dig into the stack frame and see what was actually spending time. This is a much more pretty one. And we can actually see the other thing is, so the other thing that is really good is this also intermixes userland and kernel stack traces. So like in this one, we can see that we probably, well, this is actually in recv, so that makes sense. But very frequently, you'll actually see, for example, the Ethernet card driver on top of one of these stacks, processing soft IRQs or similar. And so this is a great visualization. Chris, in his last presentation, talked about the importance of graphs and visualizations. I think the flame graph is one of my favorite, sort of quick ways to get an idea of how time is being spent. Especially what's nice is you can use perf record to record this over the course of an hour on a system, for example, and it reveals really interesting things. So yeah, and for those native tools in general, there's two people that I really recommend reading everything that they've written about this. Brendan Gregg, I've mentioned already. And his Linux performance page is great. He also wrote a book on dtrace, and he gives quite a lot of talks on sort of these subjects, mostly from maybe more of an SRE ops point of view. But I think that's a really useful point of view to adopt for actually figuring out what's happening with your Erlang applications in production. Also Giltene, just because he talks quite a lot about how to effectively measure latency. I'm mostly not going to be talking about that here, but I think it's so important. Almost every benchmark I've ever seen that involves latency has been wrong. And he points out how this is and talks about coordinated emission. These are really important ideas. Actually, that's another thing that came up in the previous talk, was just if you have a single test worker coordinating everything, you are basically going to create coordinated omission at a certain scale. So anyway, his blog and his talks can say far more about this than I can, and he's also produced or interacted with toolmakers to improve the situation. So move on to the second half. This is the biggest disclaimer. So everything that I'm going to present from here on is kind of a hack. It's a useful hack. It's a hack that works for me, but I think most of you will recognize that there's a tower of hacks involved here. And so I think the big question is how can we get Erlang stack traces intermixed with native ones, right? And usually when I propose this to people, they basically say, give me some condescending lecture about how Erlang is interpreted, and so it doesn't live on the same stack, blah blah blah. And I'm not satisfied with answers like that. So basically, a sketch of how we can actually do this. So perf events allows us to sample registers in the stack. We can unwind until we find process main, which is our real problem. We want to replace process main with whatever on the Erlang side it's actually executing. And so we actually use elf-utils for that. It has dwarf unwinding, which we'll talk about in a bit. Dwarf info gives us what registers correspond to things like the instruction pointer, the process, and that already gives us some useful information. We might also, if we're living really dangerously, walk the processes stack the way that ETP does. So ETP is the emulator toolbox for pathologists. I really highly recommend playing with this. This is a great tool for debugging. It's basically a set of GDB scripts that you can run the VM under, and they allow you to do things like print Erlang stack traces in GDB, and it's for debugging NIFs and things like that. It's super, super helpful. But it also gives us the idea of how we could walk the stack. First tool that we have here that's really handy, Linux has these syscalls, process VM, read V, and write V. They allow us to read an arbitrary process's memory without stopping it. Obviously, this is unsafe. Obviously, there are race conditions here. You can't trust anything that you're going to read from another process's memory if it's running. In fact, the memory mapping itself might disappear out from underneath us. But the good thing is it's super unobtrusive. It really has very, very little effect on the process as long as we're not reading a lot. And so that's already really helpful. And then, of course, all the dwarf information. So you must compile the VM with -GGDB ideally. There's a bunch of flags that GCC or Clang can take that really help the information they omit. This also don't worry about mixing this with optimization flags, especially if you use split debug information. There's really no performance penalty for having this debug information. It just makes your life easier, so you should always do it. Some other problems with Dwarf, though, the libraries really aren't great. Even the elf-utils libraries, libdwfl and so on, really aren't good. And you'll see the tools that I've released for this have their own vendored version of elf-utils with a few little hacks in it. Hopefully the situation will improve. Compilers are inconsistent in what they omit, and what omit actually should be emit. Of course, the problem is what they omit. And we'll see that now in a second. So, for example, some information we get from Dwarf is information about local variables. So here's a bit of the Dwarf information from process main. We can see. And we'll actually look at the process main source in a second, but we can see C_P is the current process. That's the one we're really interested in. But so you can see red's used. We've got a location for it. The location is reg12, so it's in the R12 register. That's great. So we could always, whenever we're in process main, we know that if we read R12, we can get the reductions used. Unfortunately, for C_P, we don't get that information. Although it turns out, we'll look at that code in a bit. It turns out that we actually can find the register, just GCC decided not to tell us. The other thing that's crucial is we get this unwind information, basically the call frame information from Dwarf. So this allows us to, if when we're using perf events to sample, if we happen to sample right when process main is executing, great, we'll have the registers. We don't need the unwind information. But a lot of times, we'll actually be in, say, Ertz garbage collect or something like that, and we'll want to unwind the stack until we hit process main, and then we'd like to have the registers that were active in process main. And so the CFI information allows us to do that. You can sort of see there's quite an elaborate little virtual machine that Dwarf has that sort of gets evaluated. In this case, it's actually quite simple. It's just like the register is this offset from the stack. But often it's actually a sequence of this kind of bytecode for the Dwarf sort of quasi-virtual machine. So anyway, struct process. We're quite interested in the process and what we can get out of it. A couple of important things that are useful here that we can also use for checking consistency of results that we get. CP is not so useful. I is really useful as the program counter. Stop and hand, so stop and hend are quite useful. So basically, the procedure for actually unwinding the Erlang stack is basically you start at the top of the stack and you go until hend, which is the end of the heap, looking for code pointers. And it's pretty easy from the tags to distinguish what's actually a pointer and what isn't. And so process main itself, what's really helpful here is, so as an extractive process main, we see a couple of things that are actually sort of archaically defined register with the register keyword in C. One thing that's interesting about these is actually there's actually if-defs in the ERTS code that on Spark actually assign these to fixed registers, which is probably a terrible idea. Probably trusting the compiler is better, but it would actually have really helped us if we were running on Spark. But since we aren't, but still, it turns out that GCC invariably assigns all these things to registers anyway. So reg I, reg I is the one that we're most interested in because it's sort of the current bytecode address. And if we get that, at least we have some idea of what Erlang code was executing right now. stop, of course, is handy because sort of is possibly slightly more accurate than the process's stop. And c_p, the current process, which also gets passed to the other functions that process main calls. And that's really helpful because even, well, it's something I'll comment on a bit later, but like in general, something that's useful is if your workload is divided into many small processes that kind of do small focused work, just even knowing what process was executing is actually really helpful. And actually reductions used also gets put into a register, which could be handy. I have some ideas of how to use that better, but right now I don't use it. So we want to confirm sort of where, since we don't have a register for I or CP, we want to confirm we can sort of different ways we can look at that. When we look at this disassembly, we see that, oh, you know, it looks like when we do the swap in macro, it looks like we're loading a bunch of things relative to R13 and then doing an indirect jump through RBX. So it's pretty likely that R13 is the current process and RBX is the instruction. And sort of we can confirm that sort of looking at a few other places and seeing is that consistent sort of throughout different places we look in process main. And at least in this case it is. We can see I is being assigned the return value of this, and we can see RBX is passed as the second argument, RSI, and R13 CP is being passed as the first argument, RDI, and the return value is being reassigned to RBX. So we're pretty sure I is RBX. And so this is all we need to actually do the to get quite a lot of useful information just from our perf sample. Now, if we also read from the process memory, so there's this whole concept of skid, right? In fact, perf itself, when you get a program counter value, you aren't guaranteed to get the exact program counter value. And so there's this concept of skid, which is sort of how far the PC could have moved between, you know, when some samples were taken and when you actually got this thing. And there's sort of there's all this interesting stuff. There's this PEBS stuff for getting exact instruction pointer values. That level of skid is compared to what we're about to do is nothing. So if we actually here, let me go back to yeah. So if we're sampling from the process in memory, the skid could be much worse. So this is the idea of how costly, how far away could the process have gone during the time between when we took the sample and when we're going to read from its memory. So it could be a lot. Luckily, a bunch of the values that we get do allow us to check some consistency, and especially, as I say, like if your workload is divided into many small processes, often this information is still useful, although probably you should discard samples that are older than a certain amount. This is all part of, by the way, a bias. So there are many sources of bias here, so it's important to recognize that this sampling is not unbiased, and I'll talk a bit about that after. Let me get back to how so the other thing is, now we'd actually like to integrate this into perf, the perf tool itself. So perf has support for sort of dynamic maps of symbols generated for just-in-time compilers. And so, for example, when you use perf on Java, it's customary to run a perf map agent, which basically lives in the Java VM, and whenever code is generated, it sort of spits out this map that basically is like address, length, and symbol. And that's enough for, especially in the case of Java, these addresses show up on the native call chain anyway, so perf just looks in this file to look up symbols. But we want to do the same thing for Erlang, just so that we can reuse all of perf's lookup facilities, and then we only have to patch. The only part of perf that we have to patch is the part that actually does the unwinding, so that we can ensure that we swap process main with our Erlang bytecode address. And so we generate this perf map. Now, this is somewhere where the VM could actually help us out, but at the moment I did it the hard way. So we can see in beam ranges, basically this is where address ranges for all of the modules exist, and then we have this the active code index, also the staging code index. It's like tells us which set of ranges are active right now. So all we have to do is actually peek in that. At the moment, I do it out of process with process VM readv. You could actually do this within the VM. It would be much simpler, but anyway, that allows us to write out a perf map, which then we can use and perf can use, which is really handy. And so, for example, and unfortunately it's a bit cut off, but this is like typical sampling output, and you can see we have this intermixed with, we have native calls like Ertz garbage collect and copy shallow intermixed with, like, we can see timer now diff is actually really expensive for us. I guess we do it all the time, and this was one of the first surprises from this was like, wow, that timer now diff is actually bytecode and does a bunch of math. It would actually be way faster, especially if we know we only care about small, like 64-bit values of now diff, to have this as a NIF or a BIF. But anyway, this is sort of interesting. So this is great, and this is the output of a standalone tool that I wrote called Erlang sample that does all this. There's also Erlang pstack. So this is the one that's a bit riskier. Well, Erlang sample -- pstack basically does what the pstack tool does, except that it also intermixes Erlang stack traces. This is the one where you'll get you can get all these tools. You can get a skid estimate. It'll sort of give you an idea of what was the maximum possible amount of time that could have elapsed between when you got exact samples and when you got when you read from the process memory. A lot of the times, especially if you don't need the full stack traces, the whole thing is relatively exact. But in this case, these are sort of more hazardous. But it turns out that they're actually usually pretty coherent. And I find this quite useful for getting an idea of what the schedulers are doing. And you can also have it print out what syscall the idle schedulers are working on. We talked about that. Yeah. So then integrating into perf is still not a finished affair. I did release my modifications to perf as part of all this, but they're still kind of a giant hack. Hopefully that's something I'm going to be using much more regularly, though. So I expect it will improve. This one, I'm not sure if you can see. Yeah, there's a few Erlang symbols in there, and then can actually filter just to Erlang symbols. That's really handy too, because this is kind of an overview of what the hottest sort of individual functions are, and we can actually generate flame graphs using this and so on. Just a comment about how you might use. So if this kind of unobtrusive measurement is not accurate, right? I've mentioned there are all sorts of biases that are introduced. Perf itself, how it samples sort of when it's convenient, not in a strictly unbiased way. So we know that all of this is quite biased. So what's the use of this? Well, the way that I like to do this kind of thing is establish. Well, first of all, I mean, establish some key performance indicators that are what you actually care about. Request time, bit requests per second, timeouts, things like this. These are sort of the large-scale things that you want to see these things improve. And then, basically, the tools like Erlang sample and this modified perf are really good for developing hypotheses about what could be improved in your code. And then, so I like to use this to generate hypotheses. Then in a development environment, write much more honest, accurate benchmarks and micro benchmarks that I think reflect the thing, make improvements there, and then bring them back to production and see if there's actually a correlation with these KPIs. So actually, and just one note on this, something that's really handy. So sometimes it's really hard to optimize things. So if you want to first test, is this actually a thing that affects performance? Why not, instead of optimizing it, pessimize it? This is kind of fun, is you can actually slow it down. Don't slow it down too much or you'll take down the system, just like I said. But it will still, like in many cases, you can see, okay, if this thing is hot and I add just a little bit, like a little delay, a little bit of extra work to it, yeah, I see an obvious drop in this performance indicator that I'm looking at. And this is a much faster way to test, am I on the right track, than trying to optimize something and hoping it works out, right? And I also wanted to mention Cause, this amazing causal profiler. I'm hoping someone will adapt this to Erlang at some point. Right now it's not really possible because it's very pthread dependent, but it uses this idea of intentionally introducing slowdown to simulate optimization. So it's really worth checking out. Of course, last thing about KPIs, Bjorg-Goodhart's law, when a measure becomes a target, it ceases to be a good measure. This is deeply true. And like, if you stick with the same KPIs without thinking about them, sometimes you end up with bizarrely optimized systems. I also wanted to mention rigorous benchmarking in reasonable time and related papers. Like this is like almost everything that we do. This is enough material for another talk later. So maybe I promised this talk at Erlang Factory when I talked about debugging NIFs. Maybe I'll talk about this at another conference at some point. But just the way that we do a lot of benchmarking and the statistical techniques we use are pretty much completely bogus. Calavera and Jones's paper is like one of the real foundations of a much more interesting way to do this. A few other things, just quickly. There's also a blame mode where you can say like blame and then a native symbol like Ertz garbage collect, and then it tells us, well, here are all the Erlang symbols that were most frequently seen in the stack when Ertz garbage collect was at the top of the stack, for example. And that's actually pretty helpful for a bunch of these things: copy struct, Ertz comp compound, is really nice for SIGing at least. These may be victims, they may not be the initiators, but it's still very interesting. Like in this case, you can see some BertConf and other stuff was like 10 times worse than anything else for triggering garbage collections. So that's really indicative. Allocator stats, this is something that will be in, but isn't in the release right now. Recon is awesome, Fred's tool Recon, but it is a bit heavyweight when you're trying to get the allocator stats constantly. So it turns out we can also measure those unobtrusively. And you can use ftrace to help with this too. Yeah, one last thing. So we could also sample the Erlang stack itself from perf. It's really not designed to do this, and so this is a hack too far. But of course, perf does have a facility by which it can sample arbitrary regions of memory, right? The stack. So it turns out what we can, and I did experiment with this, it does work. You can inject new threads into the VM using an if and have them set their stack pointer to the address that you want to read from, and then get perf to sample the stack, right? So that's what's going on here. But of course, that's fairly insane. So I'm hoping instead, so VPF support in the kernel is coming sort of all over things, and this is sort of has the potential to really improve use cases like this. So hacks like that will probably not be possible. There's a bunch of things that I want to do, improve the usability. Right now, the tools as released are very brittle. I'm sorry, but they're just like they've only been used by me, and they're really in a fairly almost unusable state at the moment. But hopefully, they'll improve if people actually find a use for them. I should mention KCov. There's going to be KCov integration at some point. KCov is a great coverage tool, which instead of using compiler-inserted profiling information, like you don't have to compile with -PG, instead it's sampling based. So the goal is to actually use it to integrate it with perf events and this other stuff so that you can get coverage in production, continuous coverage in production, continuous coverage information in production unobtrusively. So that's the goal there. Anyway, this is, well, I wanted to, first of all, thank my employer AdGear for sort of providing the impetus for this, all the excuses to do it, and so on. And yeah, all of this is on GitHub, and hopefully things will improve. So please, if you're interested, contact me, contribute, etc. Yeah, and thanks for listening. Yeah. Yeah, well, that's the scary thing, is when you add a delay and everything is faster, it's terrifying. But of course, it usually indicates there's some kind of contention somewhere, and or all sorts of things, or maybe that the workload needs to be spaced differently. There's like, it's really interesting. Right. Right. Yes. And just to clarify, in case it doesn't hurt, the question is just like, what about when adding a delay actually speeds things up? And of course, yeah, this is often indicative that you need to batch messages more or things like that. Other questions? Right, so the question's about microstate accounting. A little bit, and I'm really optimistic about it, because again, this is something that is much less obtrusive, is much less skewed by all the pure Erlang tools, are often skewed by things that happen kind of, especially if you have NIFs that are kind of disrupting the actual function of the VM. Microstate accounting in OTP19 promises to be at least really helpful for some of these things, but I haven't used it extensively. So, but that looks really good. Time for any more questions? Or?
One question. Yeah.
Any questions? No? Anyway, come up to me afterwards if you're interested. Thanks very much.
Thank you.